So in this lecture, I will present the proof of the strong law of large numbers. And we'll start with the lemma about sequences of real numbers. So let's say that we have xk, a sequence of real numbers, and ak, a sequence, an increasing sequence of of positive real numbers. So ak, it's less or equal than ak plus 1, and this sequence ak converge to plus infinity. Now, let's assume that the sequence, the series xk divided by ak, where we take k equal to 1 up to n, assume that these sequence of partial sums converge to some real number b. Then what I claim is that the average, well, the sum of x1 up to xn divided by an converge to 0. So this is what we want to prove. Assume that this sequence converge. If this sequence converge, then this other one converge to 0. And let me give you a proof of this statement, and let's call Bn this sum. So the sum from 1 up to n of xk divided by ak. And by assumption, this sequence converge, so let's call B the limit of this sequence. Now you see that if I take Bn and I subtract Bn minus 1, so this will be equal to xn divided by an. So if I multiply that by an, I get xn. So what we are interested in, it's the sum of x1 up to xn, but here is the definition of xn. Here is an identity for xn. So what we want to examine, it's 1 over n, which multiplies the sum from 1 up to n of xj. But xj, we have seen, it's aj bj minus bj minus 1. Observe that, well, here for n equal to 1, we have here b0, which is not defined. So by convention, I'm taking here b0 to b0. So observe that for n equal to 1, what we have is that b1 is x1 divided by a1. So indeed, if I take here n equal to 1 and I set b0 to b0, so this term is not there, and what I get is that indeed b1 times a1, it's equal to x1. So this is what I'm saying is that this object here, it's 1 over n, the sum from 1 up to n of xj, and this is the expression which we want to show that converge to 0. So let's come back here, and what I'm doing here is that I will sum by parts. So we have here a difference of b's, and I want to transfer this difference to the a's. So what I will do is that I will write this sum as, well, let's separate the terms, the two sums. So I have one which runs from 1 up to n of aj bj, and one which also runs from 1 up to n, but now it's a g bj minus 1. And what I will do is I will change variables here to write this second term as a term going from, so I want to write that as aj plus 1 bj, and now, well, j will run from 0 to n minus 1. Well, b0 is 0, so the first term is not there. So actually, I can replace here 0 by 1. And now I can make the difference. So there is one, the last term here, the term j equal to n does not appear on the other, so let me write it separately. So this is an, bn, and then what remains is a sum from 1 up to n minus 1. Aj minus aj plus 1 times bj. And, well, the first term, it's bn, and the second term, so remember that the sequence A, it's increasing, so instead of writing aj minus aj plus 1, let me write that as aj plus 1 minus aj, and I will get a minus sign here. So this is minus the sum from 1 up to n minus 1 of aj plus 1 minus aj. This is divided by an times bj. Now you see that what appeared here, it's, since if I sum, I'm considering this as weights. So if I sum the weights are all positive because A, it's an increasing sequence. And if I sum these weights, what I get is the last one, which is an, minus the first one, which is a1. So this is essentially equal to an. So what's appearing here, it's almost a convex combination of the bj's. It would be a convex combination if I add here a1 plus b0, and that would be a convex combination of the b's running from 0 to n minus 1. In any case, you see that since bn is converging to b, the first term is converging to b, these terms are, well, essentially close, they are very close to b, so they are converging to b. If they were equal to b, well, since an is converging to plus infinity, what I would get here is an minus a1 divided by an. So this is converging to 1 because an is converging to plus infinity. And therefore, that will also, we expected this to converge to b as well. So in order to complete, so remember, this sum is the sum of x, j from 1 to n divided by an. We want to prove that this converges to 0. Therefore, to complete the proof of this lemma, I have to show that this expression converges to 0. This one is converging to b. So what I need to prove is that the second term also converges to b. So I will complete the proof here. I claim that indeed this second term converges to b, and I will use the fact which I raised here, is that bn is converging to b. So if bn is converging to b, fix an epsilon positive, I want to show that the difference between this and b, it's almost, well, it's bounded by epsilon. Since bn is converging to b, this means that there exists n0 such that bj minus b is bounded by epsilon for j larger than n0. Now let me compare the sum from 1 up to n minus 1 of aj plus 1 minus aj divided by an bj minus b. So I want to write this as a sum from n minus 1 of aj plus 1 minus aj en bj minus b. So here I have b times this expression. As I said, b times this expression, so I have to add, I subtracted b, now I add b, but b times the sum of this expression, only the last term an will remain and a1, so I have here plus an minus a1 divided by an b, and then minus that b minus b. So I didn't do anything up to now. And now you see that I have here an divided by an b minus b, so that cancel. What remains here, it's minus a1 divided by a and b. So this term, I will bound it by, so I have one term which is a1 divided by an times b, which converges to 0 because an is increasing to plus infinity. And then for the sum I will divide it in two terms. First, I have the terms going from 1 up to n0. And this is aj plus 1 minus aj divided by an, bj minus b. And then the terms which are running from n0 up to n minus 1. But for these terms, I know that bj minus b is bounded by epsilon. And this is multiplied by aj plus 1 minus aj divided by an. And here I'm using the fact that the sequence a, it's increasing. So this sum in j, it's bounded by 1. So this last term, it's bounded by epsilon. So we proved that this difference, it's bounded by a sequence which converges to 0, plus a second sequence which also converges to 0, because an is increasing to plus infinity, and j, it's running from 1 to n0, so they are fixed. So as n increases to infinity, this term goes to 0, and this one is bounded by epsilon. So that proves that this expression, it's bounded, so that the limit sup in n of this expression, it's bounded by epsilon. Since epsilon is arbitrary, this proves that indeed this sequence converges to 0, and that completes the proof of the lemma. So now let me state the main theorem of this lecture. So we have a family xj of IID random variable. I'm assuming that the first moment it's finite, so that the expectation of modulus of x1 is finite, and that the expectation of x1 is equal to 0. And what I claim is that x1 plus xn divided n, that this converge almost surely to 0. So this is the statement of the strong law of large number. It's called strong because we are proving a convergence in the almost sure way. Remember that we already proved this convergence in probability, but now we are showing that actually this sequence converges to 0 almost surely. And the idea of the proof, so let me just give you the idea before I indeed prove it, it's to use the previous lemma. So in the previous lemma, if we are able to show that the sequence, the sum from 1 to n of xj divided by j, that these converge almost surely, then by the previous lemma, we will get that x1 plus xn divided by n converge to 0 almost surely. So this is what we will prove. Actually, we won't prove exactly this statement, but we will prove that j from 1 to n of xj minus a sequence bj divided by j, that these converge almost surely. From this, we will get that x1 plus xn minus b1 plus bn divided by n converge to 0 almost surely. And then we will prove that the average of the b's, actually that bj converge to 0, and therefore it will follow, since bj converge to 0, the average of bj's converge to 0, and therefore x1 plus xn divided by n also converge to 0 almost surely. So the idea is to prove that this sequence, or this sequence slightly perturbed, is summable, I mean converge, and use the lemma in order to deduce that the average of the x converge. So here is the proof. So remember that we want to prove that something like xk divided by k for k from 1 to n converge. So this is the idea. And so in order to do that, let me define yk. So a new sequence of random variables. These random variables are the variables xk divided by k bounded at 1. So this is equal to xk divided by k, and this if xk divided by k it's less or equal than 1, and this is 0 otherwise. And my claim, so what I want to prove, it's that the sequence of sums, so k from 1 up to n, of yk minus the expectation of yk, that this converge almost surely. Okay, so the first claim in this, the proof of this theorem is define yk by this formula. So you're cutting off the random variables xk divided by k at level 1. And now what I'm claiming is that the sum of yk minus its expectation converge almost surely. So let's prove this claim. To simplify notation, let me call zk the random variable yk minus the expectation of yk. So what do we know about zk? Well, by definition, the random variables yk are independent, and therefore the random variables zk are independent. So this is a sequence of independent random variables. Well, they have mean 0 by definition of zk. And therefore, to show that the sum of zk converge, what we need to prove, we need to show that the variance of zk is summable. So it remains now to show that the variance of zk, that this series is summable, and then to apply the one series Kolmogorov theorem. So let's estimate the sum of zk, the variance. Since zk has mean 0, the variance coincides with the second moment. So this is the expectation of zk square. Now zk square, by definition, this is the sum of the variance of yk. So I'm going very slowly, giving you all details. So by definition of zk, the expectation of zk squared is the variance of yk. So this is bounded by the sum of the second moment of yk. Now, by definition of yk, it's given by this expression. So this is the expectation of xk divided by k square, and this on the set in which xk it's less or equal than k. Right? So we didn't do much up to now. And now we will use the fact that the random variables xj are identically distributed to replace in this expectation xk by x1. So this is the sum for the expectation of x1. So I have 1 over k squared. And now the expectation of x1 squared. And here the indicator that x1 it's less or equal than k. I can apply Fubini to introduce the sum. These are all positive terms, so I can introduce a sum inside the expectation, and that will give me, so that this is the expectation of x1 squared times the sum. And here k, it's all k is larger than x1 of 1 over k squared. So x1, so k larger than x1. x1, it's a fixed omega, so x1 of omega, it's a real number. So here is x1 of omega. Let's assume, well, that it, so let's call j and j minus 1. So j will be the smallest integer larger or equal than x1. So I will represent that by x1. And this is, well, I'm taking the absolute value here, so x1. So this symbol, if I have a real number r, this symbol, it's the smallest integer which is larger than r. This means that if r is an integer, then this number it's equal to r, while if it's not an integer, well, it will be the smallest integer which is larger than r. And so summing over x larger, k larger than x1, or k larger than this number, it's the same thing, because here I'm taking k, it's an integer. And therefore what we have is that this is equal actually to the expectation of x1 squared. The sum now starting from this integer, which is the smallest integer larger or equal than x1 of 1 over k squared. And well, if you sum 1 over k squared starting from an integer, what you get is that this is bounded by a constant times the expectation of x1 squared. And here what I get is 1 over this integer. But this integer, it's larger or equal than x1, so this is bounded by c times the expectation of x1. And this is indeed finite, because we assumed that the expectation of the absolute value of x1 is finite. So that proves that the variance, the sum of the variance of z, it's finite. So that proves, so we just proved that the sum of the expectation of z k squared, that this is finite. So by Kolmogorov one series theorem, what we get is that the sum of zk from 1 to n converge almost surely, and zk by definition is yk minus the expectation of yk. So the claim, it's proved, and we can now go to the second step on the proof. So my second claim is that the probability that xk over k is different from yk infinitely often, that this probability is equal to 0. So yk is equal to xk over k, provided xk over k it's less or equal than 1. And now I'm saying that yk is different from xk divided by k infinitely often. This probability is equal to 0. And, well, since these events, well, what we'll do here is we will use Borel-Cantelli. So what I'm going to show is that the probability that yk is not equal to xk divided by k, that this sum is finite. If we can show that this sum is finite, then it follows from Borel-Cantelli that the probability of this event is equal to 0. But this probability, so the probability that yk is different from xk over k, is the probability that yk is 0, and this happens if and only if xk divided by k is larger than 1. So this probability corresponds to the probability that xk divided by k, it's larger than 1. And, well, this is the same thing as the probability that xk it's larger than k. Now I'm going to use again the fact that this sequence, it's a sequence of identically distributed random variables to replace here xk by x1. So this is the probability that the sum, of course, of the probability that x1 it's larger than k. And it becomes less or equal if instead of larger I get a larger or equal. And now you have to remember that we proved if we have a non-negative random variable that this sum is bounded by the expectation of the random variable. And again, the expectation is finite, and therefore this series is summable, this sequence is summable, and therefore we proved our second claim that these quantities are different infinitely with probability 0. But now, from this second claim, what can we conclude? Well, from the first claim, we know that yk minus the expectation of yk converge, almost surely. But since yk and xk divided by k are equal from one index on, if this sequence is summable, well, if this sequence converge, of course, the sequence in which I replace yk by xk divided by k, xk divided by k minus the expectation of yk, now this also converge almost surely. So you see, we are almost at the end of our problem because, well, what we want to show is that the sum of xk divided by k converge, and what we proved for the moment is that the sum from 1 to n of xk divided by k minus the expectation of yk converge almost surely. So I just copied here what we proved so far. So we proved that the sum of xk divided by k minus the expectation of yk converge almost surely. So let me just remind you what is the expectation of yk. So this is the same thing as the sum from 1 to n of xk divided by k minus, well, the expectation of yk is this expression. So this is 1 over k, the expectation of xk on the set at which xk it's bounded by k. And again, using the fact that xk or well, the sequence it's identically distributed, let me replace xk by x1 in this expression to rewrite it as the sum from 1 up to n. This is divided by k of xk minus the expectation of x1, the indicator that x1 it's bounded by k. So if I define bk as the expectation of x1 times the indicator of the set that x1 it's less or equal than k, what we have proved so far is that the sum from 1 to n of xk minus bk divided by k, that this converge almost surely. And now I'm able, at this point, to apply the lemma, and the lemma will tell me that, well, the average x1 minus b1 plus xn minus bn divided by n, that this converge almost surely to 0. And this is the same thing as saying that the average of x minus the average of b, so x1 plus xn divided by n minus b1 plus bn divided by n, that this is converging almost surely to 0. In order to conclude the proof, what I need to show is that this second term converge. In order to prove that this second term converge, it's enough to show that bj converge to 0 as j tends to plus infinity. It's clear that if a sequence tends to 0, then its average also converges to 0. So in order to prove that bj converges to 0, let's recall the definition of bj. So bj is the expectation of x1 times the indicator that x1 is bounded by j. So this is the definition of bj. Now, since x1 has finite first moment, we can use the dominated convergence theorem to say that since this expression is increasing to 1, so this term here, it's an absolute value, it's bounded by the absolute value of x1, whose integral is finite, so I can apply the dominated convergence theorem and see that as j converges to plus infinity, this expression is converging to x1. So this expectation is converging to the expectation of x1, and the expectation of x1, by assumption, is 0. So indeed, this sequence is converging to 0, and therefore x1 plus xn divided by n, it's converging to 0 almost surely, and that completes the proof of this strong law of large numbers. Now, so here's the statement of the theorem. Let me change it slightly and ask you to prove as an exercise the following statement. Assume that you have a sequence of IID random variables, but now let me take the positive part of the random variable, x1, and let's assume that this is equal to plus infinity. So this is the positive part of x1, and let's assume that the negative part of x1, that one is integrable. So this expectation is finite. And now I want you to prove that the average of x1 plus xn is converging almost surely to plus infinity. So I leave it to you to prove this as an exercise. And what I want to prove is the following proposition. Well, I will again assume that we have a sequence of IID random variables. So, and now I'm just assuming that the expectation of x1 in absolute value is equal to plus infinity. And what I claim is that, let me call Sn to be the sum from 1 to n of xj. And what I claim is that the limit sup of Sn in absolute value divided by n, it's equal to plus infinity almost surely. So the proposition complements the theorem. In the theorem, I was assuming that the expectation was finite and equal to 0. But of course, if it's not equal to 0, you just center the random variables to get strong law of large numbers in which the average of the random variable x are converging to the expectation of x. That's clear. But now what I'm assuming is that the expectation of the absolute value of x1 is plus infinity. And what we will prove is that Sn divided by n, it's in absolute value, it's converging to plus infinity. At least we have a subsequence which is converging to plus infinity. So this is saying that you have a set which has probability 1, and if omega belongs to this set, then the limit sup of Sn divided by n is converging to plus infinity. Right. So here is the proof of this proposition. So what we know is that the expectation of x1, it's plus infinity. Then this tells me that we have seen that the sum of the probability that x1 to be larger or equal than n, that this is equal to plus infinity. We have seen that this series, this sum, it's summable if and only if the expectation of x1 is finite, of the absolute value of x1 is finite. So if the expectation is infinite, this means that this sequence is infinite. And it's clear that, well, if I divide that by a, if I divided x1 by a, I still get a random variable whose expectation is plus infinity. So I can divide that by a, and I still have, by the same reason, that the probability of this expression, it's that the sum of this probability is equal to plus infinity, whatever a I choose. So let's choose a equal to some integer m. And what I have is that this sum, it's plus infinity. And let me rewrite this sum as the probability that the absolute value of x1, it's larger or equal than m times n. And this is equal to plus infinity. Well, but now since the random variables are identically distributed, I can replace here x1 by xn. So what I get is that the sum of the probability that xn it's larger or equal than mn, that this is equal to plus infinity. Since the random variables are independent, I can apply Borel-Cantelli to tell me that the probability that this will happen infinitely often, it's equal to 1. So the probability that xn divided by n, it's larger than m, infinitely often, it's equal to 1. This follows by Borel-Cantelli. So let's call this set omega m. The set omega m has probability 1. Let's take omega in omega m. And this means that xn of omega divided by n, that this is larger or equal than m infinitely often. So there are infinitely indices n for which this happens. But xn is the sum, is the difference between Sn minus Sn minus 1. And you see that if Sn minus Sn minus 1 is larger than m, this implies that either Sn divided by n it's larger than m divided by 2, or Sn minus 1 divided by n it's larger than m over 2. But if Sn minus 1 divided by n is larger than m over 2, Sn minus 1 divided by n minus 1, it's larger than m over 2. So whenever xn divided by n is larger than m, either Sn divided by n it's larger than m over 2, or Sn minus 1 divided by n minus 1, it's larger than m over 2. Since this happens infinitely many times, Sn divided by n is larger than m over 2. So it follows from this that Sn of omega divided by n, it's larger than m infinitely often. So what we proved is that for any omega in omega n, Sn divided by n, it's larger than m infinitely often. And this, it follows from since Sn divided by n, it's larger than m over 2, I'm sorry, m over 2 infinitely often. Since this happens infinitely often, this means that the limit sup of Sn of omega divided by n, it's larger than m over 2. So what we proved is that for all omega in omega m, the limit sup of Sn of omega divided by n, it's larger than m over 2. Now, if I call omega star the intersection for m larger than 1 of omega m, since each omega m has probability 1, this means that the probability of omega star it's equal to 1. Right? I'm taking the intersection, countable intersections of sets which have probability 1. So the probability of the intersection, it's also equal to 1. And if I take omega in this set omega star, since omega belongs to omega m, this means that the limit sup it's larger than m over 2. But since this holds for all m, this implies that the limit sup of Sn of omega divided by n, it's equal to plus infinity. So indeed, we proved that there exists a set which has probability 1, and that for all points in this set, the limit sup of Sn divided by n, it's equal to plus infinity. So that the limit sup of Sn divided by n, it's equal to plus infinity, almost surely, as we claimed. So I will complete this lecture with Kolmogorov Zero One Law. So assume that you have a probability space, omega, with a sigma algebra F, and a probability, and that in this family, in this set, you have a family of random variables. For the moment, no assumptions are made on these random variables. Now I want to define some sigma algebras. So assume that A is a subset of the natural numbers, which are 1, 2, and so on. And I will represent by f of A. This is a sigma algebra, and it is the smallest sigma algebra, which makes xj for j in A measurable. So it's the sigma algebra generated by the random variables xj for j in this set A. So A here might be finite or infinite. I define that. So this is the smallest sigma algebra which makes the random variables xj for j in A measurable. So it is the one which is generated by the sets sigma j minus 1 b, where j belongs to A and b it's a Borel set. So it belongs to the Borel sigma algebra. So f of A will be the sigma algebra generated by these sets, which is the smallest sigma algebra which contains these sets. So this is the definition of f of A. Now, assume that the random variables xj are independent. And fix two sets, A1, A2, which are subsets of n, and assume that they have no intersection. So the intersection of A1 and A2, it's empty. Then I claim, and I leave it to you as an exercise, to show that FA1, so the sigma algebra A1, which I defined, and FA2 are independent. Well, this means the following. If I take a set, let me call it lambda 1, which belongs to the sigma algebra FA1, and another one, lambda 2, which belongs to the sigma algebra FA2, I claim that the probability of lambda 1 intersection lambda 2, it's equal to the probability lambda 1 times the probability of lambda 2. So, well, this is an exercise, a simple exercise, and which I leave it to you. So, and here I assume that the random variables xj are independent, while in the definition of fa I didn't need it. Now we'll define a new sigma algebra, so which is the tailed sigma algebra. So if I take j less or equal than k, I will represent by fjk the sigma algebra fj j plus 1k. And here I will extend this definition to the case in which k is equal to plus infinity. In that case, fj plus infinity will be the sigma algebra generated by xj, xj plus 1, and so on. So now I introduced new notation, fjk, fj plus infinity, which are sigma algebras. Of course, you see that if I take the sigma algebra f1 infinity, this sigma algebra is generated by x1, x2, and so on. This sigma algebra is larger than the sigma algebra f2 plus infinity, because this one is generated by x2, x3, and so on. So we have here a sequence of decreasing sigma algebra, and therefore, if I take the intersection of these sigma algebras, I get a new sigma algebra. So I leave it to you again to check as an exercise, a simple exercise, that since this sequence, it's a sequence, a decreasing sequence of sigma algebras, the intersection is also a sigma algebra. And I will represent this sigma algebra by T. So this is the letter T, and it's called the tailed sigma algebra. So this is the definition of the tailed sigma algebra. So I introduced these sigma algebras and the tailed sigma algebra. Now I can state Kolmogorov Zero One Law, so a theorem. This is Kolmogorov Zero One Law. And it tells the following. So I will assume here that the random variables xj are independent. And what I claim is that if a set A belongs to the tail sigma algebra, then it is a trivial set in the sense that its probability is either equal to 0 or 1. So any element in the tailed sigma algebra has probability either 0 or 1. And the proof, it's quite simple. So let me present it. In order to show that PA is equal to 0, 1, what we will prove is that A is independent from A. So to say that A is independent from A, it's to say that the probability of A intersection A, it's equal to the product of probabilities, and therefore this is PA squared. But of course, A intersection A is A, so this is the probability of A. And since the probability of A is equal to the square of this probability, well, P, the probability of A, must be either 0 or 1. So the crux of the proof lies in this identity. We have to show that A is independent from A. And in order to do that, well, let me introduce the set M. So this is the set of all sets B in F. So remember that here we are working on a probability space omega fp. And so there is a sigma algebra, and every f and every random variable, it's measurable with respect to this sigma algebra, which appears here in my definition of the set M. And this is all sets B which are independent from A, such that the probability of A intersection B, it's equal to the probability of A times the probability of B. And what I have to prove is that A belongs to this set. So my first claim is that M is a monotone class. So that's very simple, and I will leave it to you as an exercise. So this is the first claim. Then, now, well, I claim that the sigma field F11, so remember this sigma field is a field generated by X1, that F1, it's included in M. So that all elements of F1 belong to M. So let's assume that B belongs to F11. I have to prove that B is independent from A. So now A, it's an element of the tailed sigma algebra. The tailed sigma algebra is given by this intersection. So this means, in particular, that A belongs to F2 plus infinity. And since the set 2, 3, 4, and so on up to infinity, it has no intersection with the set 1, we have seen that since the random variables xj are independent, is that these two events are independent. Right? Remember that we proved that if we have, now let me call it maybe M1. The previous take, I called that set A1, but since I have A already here, let me call it now M1. So this is a subset of N. M2, another subset of N. And if M1 intersection M2 it's equal to the empty set, then I claimed that Fm1 and Fm2 are independent. So all elements of M1, of Fm1 are independent from any element from Fm2. So and here, this is exactly what I'm using here. I have here the set 1, the set 2, 3 up to infinity. These sets are disjoint, and therefore these two events are independent, which means that indeed B belongs to the set M. Now I will repeat this argument to say that if now I take a set B which belongs to F12, it also belongs to M. So which means that the sigma algebra F12, it's contained in M. And this is for the same reasons. If I take B in F12, since A belongs to the tailed sigma algebra, it belongs to this intersection, which means that it belongs to the set F, to the sigma algebra F3 plus infinity. Since this is independent from this sigma algebra F12, this means that B, it's indeed independent from A. And more generally, if I take any J, and if I take any element which belongs to the sigma algebra F1J, I claim that B is independent from A, and this is for the same reasons, because since A belongs to the tailed sigma algebra, A belongs to the sigma algebra Fj plus 1 infinity, and therefore B and A are independent. So this means that any sigma algebra F1J, it's contained in M, and therefore I can take the union for J larger or equal than 1 of F1J. This family, it's contained in the set M. Now, this is an algebra, so let me denote by A this union. I leave it to you to check, and that's also a very simple exercise, that A, it's an algebra. And since we have an algebra contained in a monotone class by a well-known theorem, the sigma algebra generated by this algebra, it's also contained in the monotone class. Well, but what is the sigma algebra generated by this algebra? You see that, well, this algebra contains all, contains all fj, all sigma algebra generated by xj. So this sigma algebra certainly contains the sigma algebra f1 infinity, because f1 infinity, it's a sigma algebra generated by the xj for j from 1 to infinity. So, and actually you can prove that this is not just contained, but it's an identity. So the sigma algebra generated by this algebra is the sigma algebra f1 infinity. So we know now that f1 infinity is contained in M, but of course A belongs to this sigma algebra because, well, A belongs to fj infinity, so clearly A also belongs to f1 infinity, and this shows that since this set is contained in that one, A belongs to M, and this is exactly what we wanted to prove. So this shows that A is independent from A, and therefore that the probability of A is equal to 0, 1. So that's a very nice result. It tells us that the tail sigma algebra is trivial in the sense that all elements of this tail sigma algebra have a probability which is either 0 or 1. And with this result, I complete this lecture.